Let's start with a brief summary. This article, written by Paul Graham in 2002, emphasizes that programming languages have different strengths and the importance of this difference. Graham points out that the power of languages reduces the amount of code needed to create software, and thus a stronger language allows for faster software writing. Furthermore, he states that the choice of language in the software development process is often overlooked by managers, and this situation misses the opportunity to gain a competitive advantage by using a stronger and more effective language. Graham argues that the most powerful language is Lisp, and other languages are approaching Lisp but are still lacking. This article provides a deep insight into software development and language choice. Before we dive in, I want to share a quick note about how this podcast is created. As you've probably noticed, this podcast isn't voiced by a human, but by artificial intelligence. I'm obligated to inform you of this beforehand due to the rules of AI services. This podcast is made possible by our sponsor, Wope.com, an AI startup that combines content marketing with artificial intelligence to significantly boost traffic and revenue of your startups. For all the latest content, be sure to follow me at x.com yigitkoner. Now let's turn our attention back to the essay. Hashtags The Power of Programming Languages and the Resurgence of Lisp. Original title, Revenge of the Nerds. Date, May 2002. We were after the C++ programmers. We managed to drag a lot of them about halfway to Lisp. Guy Steele, co-author of the Java Spec. In the software business, there is an ongoing struggle between the pointy-headed academics and another equally formidable force, the pointy-haired bosses. Everyone knows who the pointy-haired boss is, right? I think most people in the technology world not only recognize this cartoon character, but know the actual person in their company that he is modeled upon. The pointy-haired boss miraculously combines two qualities that are common by themselves, but rarely seen together. A, he knows nothing whatsoever about technology, and B, he has very strong opinions about it. Suppose, for example, you need to write a piece of software. The pointy-haired boss has no idea how this software has to work and can't tell one programming language from another, and yet he knows what language you should write it in. Exactly, he thinks you should write it in Java. Why does he think this? Let's take a look inside the brain of the pointy-haired boss. What he's thinking is something like this. Java is a standard. I know it must be, because I read about it in the press all the time. Since it is a standard, I won't get in trouble for using it. And that also means there will always be lots of Java programmers. So if the programmers working for me now quit, as programmers working for me mysteriously always do, I can easily replace them. Well, this doesn't sound that unreasonable, but it's all based on one unspoken assumption, and that assumption turns out to be false. The pointy-haired boss believes that all programming languages are pretty much equivalent. If that were true, he would be right on target. If languages are all equivalent, sure, use whatever language everyone else is using. But all languages are not equivalent, and I think I can prove this to you without even getting into the differences between them. If you asked the pointy-haired boss in 1992 what language software should be written in, he would have answered with as little hesitation as he does today. Software should be written in C++. But if languages are all equivalent, why should the pointy-haired boss's opinion ever change? In fact, why should the developers of Java have even bothered to create a new language? Presumably, if you create a new language, it's because you think it's better in some way than what people already had. And in fact, Gosling makes it clear in the first Java white paper that Java was designed to fix some problems with C++. So there you have it. Languages are not all equivalent. If you follow the trail through the pointy-haired boss's brain to Java and then back through Java's history to its origins, you end up holding an idea that contradicts the assumption you started with. So who's right? James Gosling or the pointy-haired boss? Not surprisingly, Gosling is right. Some languages are better for certain problems than others. And that raises some interesting questions. Java was designed to be better for certain problems than C++. What problems? When is Java better and when is C++? Are there situations where other languages are better than either of them? Once you start considering this question, you have opened a real can of worms. If the pointy-haired boss had to think about the problem in its full complexity, it would make his brain explode. As long as he considers all languages equivalent, all he has to do is choose the one that seems to have the most momentum. And since that is more a question of fashion than technology, even he can probably get the right answer. But if languages vary, he suddenly has to solve two simultaneous equations, trying to find an optimal balance between two things he knows nothing about: the relative suitability of the 20 or so leading languages for the problem he needs to solve, and the odds of finding programmers, libraries, etc. for each. If that's what's on the other side of the door, it is no surprise that the pointy-haired boss doesn't want to open it. The disadvantage of believing that all programming languages are equivalent is that it's not true. But the advantage is that it makes your life a lot simpler. And I think that's the main reason the idea is so widespread. It is a comfortable idea. We know that Java must be pretty good because it is the cool new programming language. Or is it? If you look at the world of programming languages from a distance, it looks like Java is the latest thing. From far enough away, all you can see is the large flashing billboard paid for by Sun. But if you look at this world up close, you find that there are degrees of coolness. Within the hacker subculture, there is another language called Perl that is considered a lot cooler than Java. Slashdot, for example, is generated by Perl. I don't think you would find those guys using Java server pages. But there is another, newer language called Python, whose users tend to look down on Perl, and Axigen.html waiting in the wings. If you look at these languages in order, Java, Perl, Python, you notice an interesting pattern. At least, you notice this pattern if you are a Lisp hacker. Each one is progressively more like Lisp. Python copies even features that many Lisp hackers consider to be mistakes. You could translate simple Lisp programs into Python line for line. It's 2002, and programming languages have almost caught up with 1958, catching up with math. What I mean is that Lisp was first discovered by John McCarthy in 1958, and popular programming languages are only now catching up with the ideas he developed then. Now, how could that be true? Isn't computer technology something that changes very rapidly? I mean, in 1958, computers were refrigerator-sized behemoths with the processing power of a wristwatch. How could any technology that old even be relevant, let alone superior to the latest developments? I'll tell you how. It's because Lisp was not really designed to be a programming language, at least not in the sense we mean today. What we mean by a programming language is something we use to tell a computer what to do. McCarthy did eventually intend to develop a programming language in this sense, but the Lisp that we actually ended up with was based on something separate that he did as a theoretical exercise. Roots of Lisp.html, an effort to define a more convenient alternative to the Turing machine. As McCarthy said later, another way to show that Lisp was neater than Turing machines was to write a universal Lisp function and show that it is briefer and more comprehensible than the description of a universal Turing machine. This was the Lisp function eval//ses.turbifycdn.com's ti/paulgraham ttq168822195 which computes the value of a Lisp expression. Writing score eval required inventing a notation representing Lisp functions as Lisp data, and such a notation was devised for the purposes of the paper with no thought that it would be used to express Lisp programs in practice. What happened next was that sometime in late 1958, Steve Russell, one of McCarthy's grad students, looked at this definition of eval and realized that if he translated it into machine language, the result would be a Lisp interpreter. This was a big surprise at the time. Here is what McCarthy said about it later in an interview. Steve Russell said, "Look, why don't I program this eval?" And I said to him, "Ho, you're confusing theory with practice. This eval is intended for reading, not for computing." But he went ahead and did it. That is, he compiled the eval in my paper into IBM 704 machine code, fixing bugs, and then advertised this as a Lisp interpreter, which it certainly was. So at that point, Lisp had essentially the form that it has today. Suddenly, in a matter of weeks, I think, McCarthy found his theoretical exercise transformed into an actual programming language, and a more powerful one than he had intended. So the short explanation of why this 1950s language is not obsolete is that it was not technology, but math, and math doesn't get stale. The right thing to compare Lisp to is not 1950s hardware, but say, the quicksort algorithm, which was discovered in 1960 and is still the fastest general-purpose sort. There is one other language still surviving from the 1950s, Fortran, and it represents the opposite approach to language design. Lisp was a piece of theory that unexpectedly got turned into a programming language. Fortran was developed intentionally as a programming language, but what we would now consider a very low-level one. Fortran I, history.html, the language that was developed in 1956, was a very different animal from present-day Fortran. Fortran UN was pretty much assembly language with math. In some ways, it was less powerful than more recent assembly languages. There were no subroutines, for example, only branches. Present-day Fortran is now arguably closer to Lisp than to Fortran 1. Lisp and Fortran were the trunks of two separate evolutionary trees, one rooted in math and one rooted in machine architecture. These two trees have been converging ever since. Lisp started out powerful and over the next 20 years got fast. So-called mainstream languages started out fast and over the next 40 years gradually got more powerful. Until now, the most advanced of them are fairly close to Lisp. Close, but they are still missing a few things. What made Lisp different? When it was first developed, Lisp embodied 9 new ideas. Some of these we now take for granted. Others are only seen in more advanced languages, and 2 are still unique to Lisp. The 9 ideas are, in order of their adoption by the mainstream. 1. Conditionals. A conditional is an if-then-else construct. We take these for granted now, but Fortran I didn't have them. It had only a conditional goto closely based on the underlying machine instruction. 2. A function type. In Lisp, functions are a data type just like integers or strings. They have a literal representation, can be stored in variables, can be passed as arguments, and so on. 3. Recursion. Lisp was the first programming language to support it. 4. Dynamic typing. In Lisp, all variables are effectively pointers. Values are what have types, not variables, and assigning or binding variables means copying pointers, not what they point to. 5. Garbage collection. 6. Programs composed of expressions. Lisp programs are trees of expressions, each of which returns a value. This is in contrast to Fortran and most succeeding languages, which distinguish between expressions and statements. It was natural to have this distinction in Fortran I because you could not nest statements. And so while you needed expressions for math to work, there was no point in making anything else return a value because there could not be anything waiting for it. This limitation went away with the arrival of block-structured languages, but by then it was too late. The distinction between expressions and statements was entrenched. It spread from Fortran into Algol and then to both their descendants. 7. A symbol type. Symbols are effectively pointers to strings stored in a hash table, so you can test equality by comparing a pointer instead of comparing each character. 8. A notation for code using trees of symbols and constants. 9. The whole language there all the time. There is no real distinction between read time, compile time, and run time. You can compile or run code while reading, read or run code while compiling, and read or compile code at runtime. Running code at read time lets users reprogram Lisp's syntax. Running code at compile time is the basis of macros. Compiling at runtime is the basis of Lisp's use as an extension language in programs like Emacs. And reading at runtime enables programs to communicate using S expressions, an idea recently reinvented as XML. When Lisp first appeared, these ideas were far removed from ordinary programming practice, which was dictated largely by the hardware available in the late 1950s. Over time, the default language, embodied in a succession of popular languages, has gradually evolved toward Lisp. Ideas 1 to 5 are now widespread. Number 6 is starting to appear in the mainstream. Python has a form of 7, though there doesn't seem to be any syntax for it. As for number 8, this may be the most interesting of the lot. Ideas 8 and 9 only became part of Lisp by accident, because Steve Russell implemented something McCarthy had never intended to be implemented. And yet these ideas turn out to be responsible for both Lisp's strange appearance and its most distinctive features. Lisp looks strange, not so much because it has a strange syntax, as because it has no syntax. You express programs directly in the parse trees that get built behind the scenes when other languages are parsed. And these trees are made of lists, which are Lisp data structures. Expressing the language in its own data structures turns out to be a very powerful feature. Ideas 8 and 9 together mean that you can write programs that write programs. That may sound like a bizarre idea, but it's an everyday thing in Lisp. The most common way to do it is with something called a har macro. The term macro does not mean in Lisp what it means in other languages. A Lisp macro can be anything from an abbreviation to a compiler for a new language. If you want to really understand Lisp or just expand your programming horizons, I would HTML about macros. Macros in the Lisp sense are still, as far as I know, unique to Lisp. This is partly because in order to have macros, you probably have to make your language look as strange as Lisp. It may also be because if you do add that final increment of power, you can no longer claim to have invented a new language, but only a new dialect of Lisp. I mention this mostly as a joke, but it is quite true. If you define a language that has char, CDR, cons, quote, cond, atom, EQ, and a notation for functions expressed as lists, then you can build all the rest of Lisp out of it. That is, in fact, the defining quality of Lisp. It was in order to make this so that McCarthy gave Lisp the shape it has, where languages matter. So suppose Lisp does represent a kind of limit that mainstream languages are approaching asymptotically. Does that mean you should actually use it to write software? How much do you lose by using a less powerful language? Isn't it wiser, sometimes, not to be at the very edge of innovation? And isn't popularity to some extent its own justification? Isn't the pointy-haired boss right, for example, to want to use a language for which he can easily hire programmers? There are, of course, projects where the choice of programming language doesn't matter much. As a rule, the more demanding the application, the more leverage you get from using a powerful language. But plenty of projects are not demanding at all. Most programming probably consists of writing little glue programs. And for little glue programs, you can use any language that you're already familiar with and that has good libraries for whatever you need to do. If you just need to feed data from one Windows app to another, sure, use Visual Basic. You can write little glue programs in Lisp too. I use it as a desktop calculator. But the biggest win for languages like Lisp is at the other end of the spectrum, where you need to write sophisticated programs to solve hard problems in the face of fierce competition. A good example is the airline fare search program, carl.html, that ITA Software licenses to Orbitz. These guys entered a market already dominated by two big, entrenched competitors, Travelocity and Expedia, and seem to have just humiliated them technologically. The core of ITA's application is a 200,000-line common Lisp program that searches many orders of magnitude more possibilities than their competitors, who apparently are still using mainframe-era programming techniques, though ITA is also in a sense using a mainframe-era programming language. I have never seen any of ITA's code, but according to one of their top hackers, they use a lot of macros, and I am not surprised to hear it. Step. I'm not saying there is no cost to using uncommon technologies. The pointy-haired boss is not completely mistaken to worry about this, but because he doesn't understand the risks, he tends to magnify them. I can think of 3 problems that could arise from using less common languages. Your programs might not work well with programs written in other languages. You might have fewer libraries at your disposal, and you might have trouble hiring programmers. How much of a problem is each of these? The importance of the first varies depending on whether you have control over the whole system. If you're writing software that has to run on a remote user's machine on top of a buggy, closed operating system, I mention no names, there may be advantages to writing your application in the same language as the OS. But if you control the whole system and have the source code of all the parts, as ITA presumably does, you can use whatever languages you want. If any incompatibility arises, you can fix it yourself. In server-based applications, you can get away with using the most advanced technologies, and I think this is the main cause of what Jonathan Erickson calls the programming language renaissance, like byte.com/Hain21, Byte 2001 124S003. This is why we even hear about new languages like Perl and Python. We're not hearing about these languages because people are using them to write Windows apps, but because people are using them on servers. And as software shifts off the desktop and onto servers, a future even Microsoft seems resigned to, there will be less and less pressure to use middle-of-the-road technologies. As for libraries, their importance also depends on the application. For less demanding problems, the availability of libraries can outweigh the intrinsic power of the language. Where is the break-even point? Hard to say exactly, but wherever it is short of anything you'd be likely to call an application. If a company considers itself to be in the software business and they're writing an application that will be one of their products, then it will probably involve several hackers and take at least 6 months to write. In a project of that size, powerful languages probably start to outweigh the convenience of pre-existing libraries. The third worry of the pointy-haired boss, the difficulty of hiring programmers, I think is a red herring. How many hackers do you need to hire, after all? Surely by now we all know that software is best developed by teams of less than 10 people. And you shouldn't have trouble hiring hackers on that scale for any language anyone has ever heard of. If you can't find 10 Lisp hackers, then your company is probably based in the wrong city for developing software. In fact, choosing a more powerful language probably decreases the size of the team you need. Because A, if you use a more powerful language, you probably won't need as many hackers. And B, hackers who work in more advanced languages are likely to be smarter. I'm not saying that you won't get a lot of pressure to use what are perceived as standard technologies. At ViaWeb, now Yahoo Store, we raised some eyebrows among VCs and potential acquirers by using Lisp. But we also raised eyebrows by using generic Intel boxes as servers instead of industrial-strength servers like Sun's, for using a then-obscure open-source Unix variant called FreeBSD instead of a real commercial OS like Windows NT, for ignoring a supposed e-commerce standard called SET, news.com.com/210.017, that 225.723, that no one now even remembers, and so on. You can't let the suits make technical decisions for you. Did it alarm some potential acquirers that we used Lisp? Some, slightly, but if we hadn't used Lisp, we wouldn't have been able to write the software that made them want to buy us. What seemed like an anomaly to them was in fact cause and effect. If you start a startup, don't design your product to please VCs or potential acquirers. Design your product to please the users. If you win the users, everything else will follow. And if you don't, no one will care how comfortingly orthodox your technology choices were. The cost of being average. How much do you lose by using a less powerful language? There is actually some data out there about that. The most convenient measure of power is probably code size, power.html. The point of high-level languages is to give you bigger abstractions, bigger bricks, as it were, so you don't need as many to build a wall of a given size. So, the more powerful the language, the shorter the program, not simply in characters, of course, but in distinct elements. How does a more powerful language enable you to write shorter programs? One technique you can use, if the language will let you, is something called bottom-up prog.html. Instead of simply writing your application in the base language, you build on top of the base language a language for writing programs like yours, then write your program in it. The combined code can be much shorter than if you had written your whole program in the base language. Indeed, this is how most compression algorithms work. A bottom-up program should be easier to modify as well, because in many cases the language layer won't have to change at all. Code size is important, because the time it takes to write a program depends mostly on its length. If your program would be 3 times as long in another language, it will take 3 times as long to write. And you can't get around this by hiring more people, because beyond a certain size, new hires are actually a net lose. Fred Brooks described this phenomenon in his famous book, The Mythical Man Month, and everything I've seen has tended to confirm what he said. So how much shorter are your programs if you write them in Lisp? Most of the numbers I've heard for Lisp versus C, for example, have been around 7 to 10x. But a recent article about ITA in newarchitectmag.com's document/2 new 10156201444 magazine said that one line of Lisp can replace 20 lines of C. And since this article was full of quotes from ITA's president, I assume they got this number from ITA. If so, then we can put some faith in it. ITA's software includes a lot of C and C++ as well as Lisp, so they are speaking from experience. My guess is that these multiples aren't even constant. I think they increase when you face harder problems and also when you have smarter programmers. A really good hacker can squeeze more out of better tools. As one data point on the curve, at any rate, if you were to compete with ITA and chose to write your software in C, they would be able to develop software 20 times faster than you. If you spent a year on a new feature, they'd be able to duplicate it in less than 3 weeks. Whereas if they spent just 3 months developing something new, it would be 5 years before you had it too. And you know what? That's the best case scenario. When you talk about code size ratios, you're implicitly assuming that you can actually write the program in the weaker language. But in fact, there are limits on what programmers can do. If you're trying to solve a hard problem with a language that's too low level, you reach a point where there is just too much to keep in your head at once. So when I say it would take ITA's imaginary competitor 5 years to duplicate something ITA could write in Lisp in 3 months, I mean 5 years if nothing goes wrong. In fact, the way things work in most companies, any development project that would take 5 years is likely never to get finished at all. I admit this is an extreme case. ITA's hackers seem to be unusually smart, and C is a pretty low-level language. But in a competitive market, even a differential of 2 or 3 to 1 would be enough to guarantee that you'd always be behind. A recipe. This is the kind of possibility that the pointy-haired boss doesn't even want to think about. And so most of them don't. Because, when it comes down to it, the pointy-haired boss doesn't mind if his company gets their ass kicked, so long as no one can prove it's his fault. The safest plan for him personally is to stick close to the center of the herd. Within large organizations, the phrase used to describe this approach is industry best practice. Its purpose is to shield the pointy-haired boss from responsibility. If he chooses something that is industry best practice and the company loses, he can't be blamed. He didn't choose, the industry did. I believe this term was originally used to describe accounting methods and so on. What it means roughly is don't do anything weird. And in accounting, that's probably a good idea. The terms cutting edge and accounting do not sound good together. But when you import this criterion into decisions about technology, you start to get the wrong answers. Technology often should be cutting edge. In programming languages, as Iran Gat has pointed out, what industry best practice actually gets you is not the best, but merely the average. When a decision causes you to develop software at a fraction of the rate of more aggressive competitors, best practice is a misnomer. So here we have 2 pieces of information that I think are very valuable. In fact, I know it from my own experience. Number 1, languages vary in power. Number 2, most managers deliberately ignore this. Between them, these 2 facts are literally a recipe for making money. ITA is an example of this recipe in action. If you want to win in a software business, just take on the hardest problem you can find. Use the most powerful language you can get, and wait for your competitors' pointy-haired bosses to revert to the mean. Power. As an illustration of what I mean about the relative power of programming languages, consider the following problem. We want to write a function that generates accumulators, a function that takes a number n and returns a function that takes another number I and returns n incremented by I. That's incremented by, not plus. An accumulator has to accumulate. In Common Lisp, this would be dfun foo n, lambda I, inf n I, and in Perl 5, sub foo my n equals at, sub n plus shift, which has more elements than the Lisp version because you have to extract parameters manually in Perl. In Smalltalk, the code is slightly longer than in Lisp. Foo n s s n s equals plus I. because although in general lexical variables work, you can't do an assignment to a parameter, so you have to create a new variable s. In JavaScript, the example is again slightly longer, because JavaScript retains the distinction between statements and expressions, so you need explicit return statements to return values. Function foo_n, return function I, return n plus I. To be fair, Perl also retains this distinction, but deals with it in typical Perl fashion by letting you omit returns. If you try to translate the Lisp, Perl, Smalltalk JavaScript code into Python, you run into some limitations. Because Python doesn't fully support lexical variables, you have to create a data structure to hold the value of n. And although Python does have a function data type, there is no literal representation for one, unless the body is only a single expression, so you need to create a named function to return. This is what you end up with. Def foo_n s equals n, def bar I s0 plus equals I return s0, return bar. Python users might legitimately ask why they can't just write def foo_n return lambda I, return n plus I, or even def foo_n lambda I, n plus equals I, and my guess is that they probably will one day. But if they don't want to wait for Python to evolve the rest of the way into Lisp, they could always just... In OO languages, you can, to a limited extent, simulate a closure, a function that refers to variables defined in enclosing scopes, by defining a class with one method and a field to replace each variable from an enclosing scope. This makes the programmer do the kind of code analysis that would be done by the compiler in a language with full support for lexical scope, and it won't work if more than one function refers to the same variable, but it is enough in simple cases like this. Python experts seem to agree that this is the preferred way to solve the problem in Python, writing either def foo_n, class ack, def score init, self s, self.s, def inc self I, self.s plus I, return self.s return ack n, in C or class foo, def score init self n, self.n equals n, def score call self I, self.n plus equals I return self.n. I include these because I wouldn't want Python advocates to say I was misrepresenting the language, but both seem to me more complex than the first version. You're doing the same thing, setting up a separate place to hold the accumulator. It's just a field in an object instead of the head of a list. And the use of these special, reserved field names, especially or call, seems a bit of a hack. In the rivalry between Perl and Python, the claim of the Python hackers seems to be that Python is a more elegant alternative to Perl. But what this case shows is that power is the ultimate elegance. The Perl program is simpler, has fewer elements, even if the syntax is a bit uglier. How about other languages? In the other languages mentioned in this talk, Fortran, C, C++, Java, and Visual Basic, it is not clear whether you can actually solve this problem. Ken Anderson says that the following code is about as close as you can get in Java. Public interface intoint, public int call int I. Public static intoint foo, final int n, return new intoint, int s equals n, public int call int I, s equals s plus I, return s. This falls short of the spec because it only works for integers. After many email exchanges with Java hackers, I would say that writing a properly polymorphic version that behaves like the preceding examples is somewhere between damned awkward and impossible. If anyone wants to write one, I'd be very curious to see it, but I personally have timed out. It's not literally true that you can't solve this problem in other languages, of course. The fact that all these languages are Turing equivalent means that, strictly speaking, you can write any program in any of them. So how would you do it? In the limit case, by writing a Lisp interpreter in the less powerful language. That sounds like a joke, but it happens so often to varying degrees in large programming projects that there is a name for the phenomenon, Greenspun's 10th rule. Any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Common Lisp. If you try to solve a hard problem, the question is not whether you will use a powerful enough language, but whether you will A, use a powerful language, B, write a de facto interpreter for one, or C, yourself become a human compiler for one. We see this already beginning to happen in the Python example, where we are in effect simulating the code that a compiler would generate to implement a lexical variable. This practice is not only common, but institutionalized. For example, in the OO world, you hear a good deal about patterns. I wonder if these patterns are not sometimes evidence of case C, the human compiler, at work. When I see patterns in my programs, I consider it a sign of trouble. The shape of a program should reflect only the problem it needs to solve. Any other regularity in the code is a sign, to me at least, that I'm using abstractions that aren't powerful enough. Often that I'm generating by hand the expansions of some macro that I need to write. Notes: the IBM 704 CPU was about the size of a refrigerator, but a lot heavier. The CPU weighed 3,150 pounds, and the 4K of RAM was in a separate box weighing another 4,000 pounds. The Sub-Zero 690, one of the largest household refrigerators, weighs 656 pounds. Steve Russell also wrote the first digital computer game, Space War, in 1962. If you want to trick a pointy-haired boss into letting you write software in Lisp, you could try telling him it's XML. Here is the accumulator generator in other Lisp dialects. Scheme, define foo n, lambda I, set n plus ni n, goo, df foo n, op inf n, arc, def foo n plus plus n. Iran Gat's sad tale about industry best practice at JPL inspired me to address this generally misapplied phrase. Peter Norvig found that 16 of the 23 patterns in design patterns were invisible or simpler, h//norvig.com/design/pattern/ in Lisp. Thanks to the many people who answered my questions about various languages and or read drafts of this, including Ken Anderson, Trevor Blackwell, Iran Gat, Dan Giffen, Sarah Harlan, Jeremy Hilton, Robert Morris, Peter Norvig, Guy Steele, and Anton van Straten. They bear no blame for any opinions expressed. Many people have responded to this talk, so I have set up an additional page to deal with the issues they have raised. Revenge of the Nerds. It also set off an extensive and often useful discussion on the ELL1's ai.mit.edu's LL1 Discuss Archived HTML threads.ml mailing list. See particularly the mail by Anton van Straten on semantic compression. Some of the mail on LL1 led me to try to go deeper into the subject of language power in power.html. A larger set of canonical implementations of the accumulator generator benchmark, acgen.html, are collected together on their own page.